Greetings and salutations, everybody. This is Jacob. Okay, so how do we go about solving this problem? It seems discombobulating, you say. Well, my friends, take a number and have a seat, because you're not the only one that can't make heads or tails of this problem. Oh no. Usually I only pose problems that I've wrestled with for quite some time myself. Oh yes. Alright, I'll just get into it. I'll save the blabbering for the end of the video, my friends. Let's start out by giving some definitions, like we usually do. R is the radius of the semicircle, as stated on the thumbnail. 2r is the total length of the stick. Omega is the angular velocity of the stick, measured in rads per second. U of A is the speed of point A when it makes contact with the semicircle. And U of B is the speed of point B when point A comes into contact with the semicircle. Okay, so how do we find the speed of point B when point A comes into contact with the semicircle? First, we have to find the speed of point A when it comes into contact with the semicircle, correct? Before we do that, we can do nothing. So as the stick is sliding down the semicircle, the stick is simultaneously moving and rotating about A. In other words, the stick is translating and is rotating around a fixed axis that is perpendicular to the plane of motion. And this axis goes through the endpoint A of the stick. In other words, if we were to put an observer at point A, and to that observer, all the other particles of the stick would look like they're moving on a circle that revolves around that observer, my friends. So that's the basics of the kinematics of a rigid body. If you've taken a course in statics and dynamics in college or at university. So what is the only point on the stick that's only translating? It's the endpoint A, correct? All the other points are translating and rotating around A. Okay, so now what do? Since there's no friction between any surfaces, as already stated in the initial conditions, what does that imply? It means we can use the principle of conservation of energy on this rigid body here, since no energy is being lost through heat. In other words, only conservative forces are working on this rigid body. Conservative force is a force whose work being done on the body is independent of the path taken. It only depends on the initial and final position. Such forces are gravity, elastic force, electrical force, for example. So we apply this principle, but where do we apply it? To point A, to point B? This is a caveat, my friends. This is where the trickiness starts, my dudes. Remember, we're dealing with a rigid body, not a point mass. So we have to apply the principle of conservation of energy to the center of mass of the rigid body, not just anywhere. Oh yes. And in the context of this thin rod, where is the center of mass? It's at the half point, mid-length, correct? We're assuming this thin rod, or stick, has a uniform density throughout its length. I probably should have stated it explicitly on the thumbnail, but I'm sure most people attempting this problem would assume it, so no biggie. So, the formula for the conservation of energy of a rigid body, not a point mass, is this one right here. Total initial potential energy plus total initial kinetic energy equals total final potential energy plus total final kinetic energy. So what the heck is the total potential and total kinetic energy of the rigid body, you ask? How does that differ from the regular potential and kinetic energy? Good question. If you recall, the formulae for the regular potential energy of a point mass are m times g times h, where h is the distance of the particle from the ground, and the kinetic energy is 1/2 times m times u squared, where u is the speed of the particle. The total potential energy is the sum of all the potential energies of all the particles of the rigid body. And we find that by treating the rigid body like a point mass situated at the center of mass of the rigid body. So the formula for that is m times g times hc, where hc is the height of the center of mass from the ground, and m is the mass of the entire body. And the total kinetic energy of the rigid body is this formula here, 1/2 times m times uc squared plus 1/2 times I of c times omega squared, where u of c is the speed of the center of mass, m is the total mass of the rigid body, And omega is the angular velocity of the body, as we discussed earlier. But what is this I see here? What the heck is this, you ask? This is what we call the moment of inertia of a rigid body. So the moment of inertia basically describes how difficult it is to change the angular velocity of a body, much like how a mass describes how difficult it is to change the particle's translational speed. The moment of inertia depends on the axis of rotation as well as the density and mass of the body and its overall shape. A particle doesn't have rotational speed, only translational speed. A point can't rotate around itself, for example. It only has translational speed. So this particular moment of inertia is about the center of mass, specifically, which is at the midpoint of the thin rod or stick. And there's a formula for this moment of inertia of a thin rod about the center of mass, and that is 1/2 times m times L squared, where m is the mass of the rod and L is the length. Since the rod starts sliding from rest, then the total initial kinetic energy is 0. And so we apply our conservation of energy formula, and we have m times g times initial height equals 1/2 times m times um squared plus 1/2 times I of m times omega squared plus m times g times h of f, which is m times g times h of I equals 1/2 times m times squared plus 1/2 of 1/12 times m times 2r squared times omega squared plus m times g times h of f. We do the calculations and all the algebraic operations. We solve for u of m, and we end up with u of m squared equals 2 times g times the height differential, hi minus h of f, minus 1/3 times r squared times omega squared. So we put this formula aside for the moment because we need to find the initial and final height of the midpoint. We'll start with the initial height. So looking at this triangle here, it's easy to see that initial height equals r times sine of 45 degrees, which is square root of 2/2 times r. Okay, so what's the final height? It's the height of the midpoint when endpoint A comes into contact with the semicircle, correct? But where does the particle A come into contact with the semi-cylinder? Here's the other tricky part of the problem. It's tempting to assume that it comes into contact at the same point that the midpoint came into contact with the semi-cylinder. That's not the case, my friends. As we've already seen, this stick is always tangent to the circle as it slides down the semicircle. So at the very moment that particle A touches the semicircle, the stick will be tangent to the circle. So as you see here, this angle here is 90 degrees, and this side here is r, and this side here is 2 times r. Since we have at least 2 sides and 1 angle of this triangle, then we can find this angle here, theta. First we'll use the Pythagorean theorem to find the hypotenuse of this triangle, x, which is x squared equals r squared plus 2r squared, which is x squared equals 5 times r squared, which is x equals square root of 5 times r. Now we use the law of sines, and we have sine of 90 over square root of 5 times r equals sine of theta over 2 times r, which is sine of theta equals 2 times r times sine of 90 all over square root of 5 times r. And the r's cancel out, and we have theta equals arc sine of 2 over square root of 5, which is approximately 63.43 degrees. Okay, now that we found this angle here, theta, we can find the final height of the midpoint. This angle here is also 63.43 degrees, and so is this one. And so we have h of f of m equals r times cosine of 63.43, which is 0.447 times r. Okay, so now that we found the heights, we plug those values into our conservation of energy formula, and we get u of m squared equals 5.096 times r minus 1/3 times r squared times omega squared. Okay, so now what the heck do we do? So now we use the kinematics of a rigid body formula, as we discussed earlier, and the formula is u of b equals u of a plus u of b with respect to a, where u of b is the speed of a random particle on the body, u of a is the speed of the particle that's only translating, and u of b with respect to a is the relative speed of particle b with respect to a. And this is given by the formula u of b with respect to a equals omega times r, where r is the distance of the particle from the axis of rotation. So far so good? Let me repeat that for the people in the back. U of b with respect to a, the direction of it is tangent to the line connecting a and b. In other words, it's the rotational component of the mass's total speed. We good now? All right, moving on. So this diagram here depicts our physical situation perfectly so far. This here is the total speed of the midpoint. This here is the rotational component, which is perpendicular to the distance vector. And this is the translational component. As we said earlier, the instantaneous speed of particle A lies on the distance vector. So using the Pythagorean theorem, we have u of a squared equals u of m squared minus u of m with respect to a squared. And we solve for u of a, and we end up with u of a equals square root of 5.096 times r minus 4 over 3 times r squared times omega squared. Okay, so now we know u of a. Now we go to particle B. And this diagram here depicts particle B's situation to a t. And since the direction of particle B's speed is parallel to the ground at all times, we know this angle here, which is 26.57 degrees. So tangent of 26.57 equals u of b with respect to a over u of a, which is 2 times omega times r over square root of 5.096 minus 4 over 3 times r squared times omega squared. And we solve for omega, and we do the calculations and all that jazz. And we end up with omega equals 1.954 over 3.6 times the square root of r. And we plug that in our u of a expression, and we end up with u of a approximately 2.236 times square root of r. And so now we can find u of b, which is u of b equals u of a over cosine 26.57 degrees equals 2.236 times square root of r over 0.8943, which is approximately 2.5 times the square root of r. And that's all she wrote, my friends. 2.5 times the square root of r. Quite an intuitive answer, if you ask me. Oh yes. Wow, what a problem, you guys. Like the secretary problem, this problem kicked my butt as well. I had to redo my calculations and the audio for this video twice. Both of them twice, my friends. Not just once, or not just one of them. So this really kicked my ass, my dudes. I don't mind redoing calculations and all that jazz, but having to redo the audio as well is very tedious work. At least with the secretary problem, even though I was redoing calculations over and over again, I only did the audio once. But with this one, man, this one really kicked my butt. Right now I'm working with 3 audios here as we speak. So I have to figure out the parts of the previous audio that are correct and only redo the wrong parts. It's easier to just start over and do things from scratch. And it's like digging a bunch of holes in the ground and trying to remember which one was the original hole. Oh yes. But tediousness aside, this really is an exceptional problem. I'm glad I came across it in my problem searching escapades. I just wish I had nailed it the first time, not have to do it over and over again, plus the audio of it. Or at least not the audio, which is the tedious part of it. But of course, it's preferable to do stuff like this than to upload something that's just flat out wrong, correct? C'est la vie. Such is life, as they say. I mean, if you don't occasionally bite off more than you can chew, then how the heck can you take your abilities to the next level? There's no way. Oh yes. So let me know in the comments section if you liked this puzzle, if you found it difficult, if you solved it another way. You know, I was debating to pose another problem instead of this one because I couldn't make heads or tails of it at first. But I'm glad I didn't quit and settle for a lesser problem. Because of my persistence, we have this marvelous problem in front of us, my friends, to take apart and dissect and enjoy. Oh yes. So the moral of the story is don't quit on a problem at the first sign of trouble. Let your subconscious chew on it a bit before moving on. So that's pretty much it, my friends. Take care, you guys. Smash those buttons like there's no tomorrow. Shoot a puzzle suggestion my way. I'm more than happy to showcase a puzzle that you're interested in seeing the solution of, my friends. Pretty much it, and I'll see you guys in the next video. Bye-bye.